Hello, mathematicians. We are going to talk today about using complex numbers to basically multiply them and divide them. And that's pretty much what we're doing here. We're finding products, multiplying them, quotients, dividing them, and we're using DeMoivre's theorem, which is pretty much multiplying them, but it's really dealing more with powers. Now, we're talking about complex numbers that are in polar form. So we're looking at things like this. Find the product of the complex numbers. And these z's are just something to stand for the number, just a way to just give it an identity. This number we're going to be calling z sub 1, and this number z sub 2. Okay, and we really don't even need that for this because I'm going to show you how simple this really is. Basically, when I am multiplying, which is what product means, here's how I do it. Now notice these are both in polar form. Remember, in polar form, the number out front is r, and that's actually also called the modulus. And then the angle is theta. That's also called the argument. So what we're going to do is we're going to take the moduli, there's two of them, the r's, and we're multiplying here. We're going to multiply those. So that's very straightforward. We're going to multiply those. But the angles we're going to add. So that's how this works. I'm going to do 3 times 7 out front, and then times is cosine of 36 plus 24. 36 plus 24 plus I, and the same thing for sine. 36 plus 24, and then I'll simplify, and that gives me 21 times the cosine of 60 plus I times the sine of 60. And that's honestly all there is to it. Now, you have to pay attention to how you're asked to give your answer. The problems I'm looking at say leave your answer in polar form, so that's what I would do, is leave my answer in polar form. Sometimes they might want me to simplify, like I know the cosine of 60, I know the sine of 60, so I might be asked to change that to rectangular form. And so this is polar form, let's just say if I wanted to leave it in polar form, I would stop there. If I want to put that in rectangular form, I would go ahead and say, well, that's 21 cosine 60 plus 21 sine 60 all times I. This is 21 times the cosine of 60 is 1/2. 21 times the sine of 60 is root 3 over 2. And so I would have 21 halves plus 21 root 3 over 2 times I. So that would be the same answer in rectangular form. So if you're asked to go to rectangular form, or maybe it's multiple choice and you can see that the answers are in rectangular form, then this is where you'd want to end up. If you're asked to go to polar form, or you can see that the answer choices are in polar form, that's where you would end up. Okay, so now what I did again was this times this out front, and this plus this here. This is not the first time we've seen where multiplication has a relationship to addition. Happens a lot. So here's the actual formula to see it written out. And this is basically what I did right here. I took my R1 times my R2, and I added my theta 1 and my theta 2. So this is R1, R2, theta 1, theta 2, etc. Okay, so that's the formula. So let's go ahead and use that formula again on another problem. This one says, and this one is in radians. My argument is in radians. Find the product. Okay, so now again, this is my formula. And I need to multiply my moduli, my two moduluses, so to speak, but I don't have any. So this is like, if I don't have anything there, that's just like if it says 1. 1 times all of this, 1 times all of that. So it's just 1 times 1 out front. So I don't have to worry about that. What I do have to worry about is adding my arguments. So basically I'm going to have cosine of pi over 6 plus pi over 4 plus I times the sine of pi over 6 times plus pi over 4. And again, if I had numbers out front, if it was like 2 and 3 out front here, I'd do 2 times 3 out front here. I just don't have any. Okay, so when we add fractions, we need a common denominator. So my common denominator here is going to be 12. So 1 pi over 6 is 2 pi over 12. 1 pi over 4 is 3 pi over 12. So when I add these, I'm going to get 5 pi over 12. And again, the directions for the ones I'm doing say leave in polar form. And in this one, it's a little bit easier to leave it in polar form because that's not a unit circle value. So I would have to go to the calculator or maybe do some sum and difference formulas or something a little bit more complicated to get to rectangular form. All right, so that's all there is to the product formula. The quotient formula, same exact idea, except the numbers out front are divided because that's what quotient means. And the numbers that are my argument, the numbers out front, remember modulus, the arguments, instead of added, they are subtracted. So I'm going to do 20 divided by 4 times cosine of 75 minus 25 plus I times sine of 75 minus 25. All right, and here's the formula written out. Looks very similar. Z sub 1 divided by Z sub 2 is just R sub 1 over R sub 1 divided by R sub 2 times the cosine of the difference in their arguments. Okay, and I just focused that a little bit. Hopefully that's a little better. So that means I'm going to do 20 divided by 4, that's 5. 75 minus 25 is 50. So 5 times cosine of 50 plus I times sine of 50. And that's my answer in polar form. Okay, now if I were to do it, change it to rectangular form, I would end up with decimals here. I would definitely have to get decimal approximations because those aren't unicircle values. So I'm going to go with what my problems asked me to do and just leave it in polar form. Okay. Now I am fighting with my cat over the next problem I wanted to show you because he was sitting on it. But here it is. Find the quotient. Same thing. Same formula. Only difference was I wrote the two numbers, the two complex numbers side by side, just for space. So I'm going to divide the r's, so 3 divided by 4, and I'm going to subtract my angles. So pi over 5 minus pi over 10. So it's going to be z sub 1 over z sub 2 equals 3 over 4 times the cosine of pi over 5 minus pi over 10 plus I times the sine of pi over 5 minus pi over 10. And that's my answer, but I can simplify it. So I will. Pi over 5, common denominator, remember to divide in, to add or subtract fractions. So pi over 5 is the same thing as 2 pi over 10. Minus 1 pi over 10, that's just going to leave me with pi over 10. So cosine pi over 10 plus I sine pi over 10. And whatever you're doing here is exactly the same thing here every single time. So once you've figured out how to simplify this, you also know how to simplify this. So there it is in polar form, and I'm going to go ahead and leave my answer just like that. All right, so now we move on to that hard to pronounce one, DeMoivre's theorem. I can't do it perfectly. I could do it, I think, better than some perhaps, but only because I took high school French. DeMoivre's theorem is probably my best. That's the best I'm going to get. If you are French, I apologize. I probably just butchered it. But basically, DeMoivre's theorem asks us to do powers of a complex number that is given in polar form. So instead of having two different ones, we have one number and we're raising it to a power. Now here's the thing I want to point out to you. We know what a power is. We know what using a power does. Here I was taking two different numbers and multiplying them. The difference here is it's like I'm taking one number, but I'm multiplying it 3 times. So this is really, and let's see if I can fit these all in here. I'm not real confident that I can, but if I write small, maybe I can. It's really, yeah, I should have had more faith in myself. And I also shouldn't have spoken too fast, too soon. I'm getting close to the edge. Okay, made it. That's what that is. That's what it means to do something to the third power. So really, here, I'm just using the product rule that I used before. So I'll do 2 times 2 and 10 plus 10. Okay? But then I'll have that answer, and I'll have to take that answer, and I'll have to multiply the number up front times 2 and add this plus 10. So 2 times 2 here is 4. 10 plus 10 gives me 20. Then I'm going to take that 4 and multiply it times 2 and take the 20 and add 10. So basically all that's happening is I'm multiplying the number out front however many times I have it. So basically that's this number, the 2, gets raised to the third power. And the 10, I'm adding however many times I have it. So that's cosine of 3 times 10 plus I times sine of 3 times 10. So this exponent basically affects the number out front by raising the number to that power. So this becomes 2 to the third. And here, since we're adding 10 however many times we've got it, it's 3 times 10. It's not going to be a power, it's going to be that many times. So this becomes 8 times the cosine of 30 plus I times the sine of 30. And you'll notice that this one says write your answers in rectangular form, and those are unit circle values, so I know the cosine of 30. So this is 8 times square root of 3 over 2 plus I times 1/2, which is 8 times the square root of 3 over 2 is going to be 4 root 3 plus 1/2 I. And there it is in rectangular form, and that's my final answer. So now, looking back at what we did again here, we took the number out front and raised it to the power. We took the argument and multiplied it times that number. So here's how that looks. Right there. That's what we're doing there. If you have a complex number to the nth power, then your number out front, your radius, gets multiplied or gets raised to the nth power, and your argument gets multiplied by that n, that number n. All right, let's do one more like that. This is a little bit messier looking one. We have a radical and we have some radians instead of our degrees. So let's go ahead and use that formula. Here is my n. That's what I'm doing, is I'm raising this entire number to the nth power, where n is 6. So I'm going to take the radius and I'm going to raise it to the 6th power. And then I'm going to take my arguments, and I'm not going to raise them to the 6th power. I'm going to multiply them by 6. So this is cosine of 6 times 5 pi over 18 plus I sine 6 times 5 pi over 18. All right, so we have some things to simplify here. First off, the square root of 3 raised to the 6th power. If you have a square root and you square it, then it's gone, right? So let's just think through what's happening here. Let me grab a piece of scratch paper. Square root of 3 6 times. You don't have to draw it out necessarily, but you can maybe think it out. For every 2 that I have, that's just 3. So 3 times 3 times 3, which is 27. So this is going to become 27 out front. Then I have to think about simplifying 6 times 5 pi over 18. Anytime you have just a plain old number, not a fraction, times a fraction, remember that your number is over 1. So you're really just multiplying it times the numerator. So this is 6 times 5 on top, 18 on the bottom. Those are both divisible by 6. So this goes 5 times here and 3 times here. I could have simplified maybe there, cross-canceled. And I get 5 pi over 3. So that's what I'll have here for both of these. Cosine 5 pi over 3 plus I sine 5 pi over 3. And at this point, you're probably starting to recognize the fact that you're starting to recognize your unit circle values when you see them. Hopefully you have been for a while. And this is 5 pi over 3. It's a unit circle value. That's basically, back with the scratch paper, fourth quadrant, 30 degrees from here, 60 degrees from here, so to speak. Okay, so that value is, let's see, 1/2 for cosine and negative root 3 over 2 for sine. So 27 times the cosine of 5 pi over 3, that's 1/2, plus 27 times the sine of 5 pi over 3, which is negative root 3 over 2, all times I. This is putting it in rectangular form because we were asked to. So we get 27 halves plus, or I should have written minus really, because it's a negative, 27 root 3 all over 2I. Having trouble moving my paper up. There's a computer speaker in the way. But that is that. We have our 3 formulas, product, quotient, and DeMoivre's theorem, and we know how to do them all now. So I hope this was helpful, and I hope you enjoy your homework now because you know exactly how to do it. Thanks for coming. See you again soon, hopefully.